For decades, application security relied on a simple premise: keep bad data out. But when securing an AI system, those rigid barriers dissolve. Look at a standard web application. It relies on a strict firewall, a physical trust boundary. Now compare that to a modern large language model built on the transformer architecture. Its intake mechanism is a single, open context window. In traditional apps, user inputs are strictly separated from execution logic. Web forms strip malicious code before reaching the database. But in an LLM, that separation collapses. Secure developer instructions and untrusted user input are poured into the exact same space. The self-attention mechanism evaluates all text using the exact same math. Each token generates query, key, and value vectors, computing their dot product for a weighted score. There is zero architectural difference between safe guidelines and malicious exploits. It flattens both identically. Exploiting this flaw requires moving up an escalation ladder. An AI red teamer attacks the raw model layer, poisons data retrieval pipelines, and hijacks system orchestration. Prompt injection remains a permanent architectural reality of modern LLMs, rather than a temporary software bug that can be patched. We start at the model layer. To make LLMs safe for public use, developers apply reinforcement learning to restrict harmful outputs. This creates an alignment tax, a constant friction between the model's raw pre-trained knowledge and its artificial safety constraints. An AI red teamer's first objective is to systematically circumvent this safety alignment layer to reach the unrestricted capabilities of the raw model weights. Basic single-prompt jailbreaks are easily caught by modern filters. Instead, attackers use crescendo attacks, which span multiple turns. They start with a benign topic and slowly escalate, bypassing filters that only evaluate single messages in isolation. To scale these attacks, red teamers use the pair framework, pitting one LLM against another. The attacker model fires a prompt, gets blocked, and automatically iterates. This loop runs thousands of times at machine speed, eventually forcing a bypass of the target's safety guardrails. The most sophisticated attacks abandon language altogether, using adversarial suffixes constructed of pure mathematics. Appending a string of high-perplexity characters to a prompt mathematically forces the model's probability distribution away from safety training and into restricted territory. These token sequences are discovered by analyzing the model's internal weights through gradient-based optimization, and the resulting suffixes frequently work across entirely different AI models. Because safety alignment is merely an overlay on top of capable weights, automated mathematical attacks will consistently find a way to strip that overlay away. Once the model is compromised, the target shifts from isolated chatbots to enterprise data. This is where retrieval-augmented generation, or RAG, enters the picture. RAG architecture allows the LLM to pull information from external vector databases and the live internet, supplementing training data. This creates a vector for indirect prompt injection, where the attacker targets external data sources rather than the model itself. Malicious instructions hidden on a website, inside a job applicant's resume, or an internal company wiki. The RAG system retrieves this poisoned document and drops it directly into the LLM's context window, bypassing initial security filters. The data pipeline flows both ways, which also creates severe extraction risks. Attackers can systematically probe the model's parametric memory, searching for data points that were heavily repeated during training. If successful, they can force the AI to spit out verbatim personal data or hard-coded API keys. They can even target the vector database itself using embedding inversion, a mathematical technique that reconstructs private documents from the seemingly anonymous number arrays stored inside the system. Securing an enterprise deployment requires treating every single piece of external data as a potential exploit waiting to be executed. The final, most critical layer of the escalation ladder is orchestration. When you turn an LLM into an autonomous agent, you give it the ability to execute commands in the real world. Agents typically use a react architecture, a continuous loop where the model reasons about a problem, formulates a plan, and then invokes actual software tools to execute that plan. This creates the confused deputy problem. The AI has authority to delete databases, but lacks judgment to recognize when an attacker pulls the strings. Agents connect to tools via the Model Context Protocol, bridging the LLM with file systems and APIs. Attackers exploit this via tool poisoning. A compromised server feeds a deceptive text description back to the model, hijacking its entire routing logic. This vulnerability enables the most severe orchestration exploit, the rug pull attack. The attack exploits the gap between approval and execution. A malicious server presents a harmless tool description, like fetching weather data, and the user approves. Milliseconds later, the server overwrites the behavior. The invoked tool quietly executes a command exfiltrating your private data. AI agents attach the theoretical danger of text manipulation to live production systems, maximizing the potential blast radius of a single bad prompt. We have now traced the attack path from the foundational model weights through the RAG data pipelines all the way to external MCP orchestration. Because prompt injection is a structural reality, you can't secure deployments by tweaking prompts. Mitigation requires strict defense in depth, building independent security layers entirely outside the LLM's cognitive loop. First, deploy perplexity filtering at the gateway to block adversarial suffixes. Second, replace rule-based filters with dedicated input and output guardrails that analyze data semantics. Third, enforce strict container isolation for all connected tools. If a single MCP server is poisoned, it must be partitioned from the host file system. Fourth, neutralize rug pull attacks by verifying tool behavior at the exact moment of execution. Finally, install mandatory human-in-the-loop circuit breakers on any agent pathway capable of performing an irreversible, high-risk action. The objective here is not to build an unhackable language model. Attempting to do so ignores the underlying architecture of the technology. True AI security means assuming the model will eventually be compromised and architecting the surrounding system to rigorously contain the blast radius when it happens.